is maybe a side discussions. This one is about how to use MATLAB's command step to help us for drawing the response of the systems to different commands. Basically, in this slide, I'm using this example. Okay, so this is the transfer functions. And so output equal to the transfer function multiplied with input. So that is the problem statement. And then from here, I list 1, 2, 3 examples and corresponding to your unit step in response, which means R. This one is the magnitude R equal to 1 in time domain. And unit impulse, so that basically in the time domain, that is a pulse and unit ramp. The 1, 2, 3 are the three typical responses we use in traditional controls for analytical solutions. And so I'm using the three examples to demonstrate how to use the same command. You can see I use the same step command. And how can we use those ones to calculate the response by MATLAB. This is the standard form for from the MATLAB. Basically here, this is a problem statement. If we're going to calculate the time, the C of t, the response of C in the time domain, however, that one is given in this form. Basically, the step is to calculate, this command is to calculate, take up the numerator and denominators of this. Numerator is 2 and 1. Okay, you can ignore the 0 here. And denominator is 1, 1, 1. So simply you leaving one of us outside the description of this polynomial. Keep this in mind. Okay, right now I'm talking about the syntax of the program. It's not about the science, technology, or anything. I'm talking the syntax. Syntax, that means the rule you have to memorize. Okay. So basically here again, the step. This one, if you want to calculate step using the step, basically is this. You form any polynomial functions and you're leaving one of us outside, then leaving this out, then basically you describe in the numerator denominator is by this one. Okay, keep this in mind. Okay, now back to our unit impulse. And given our systems like this, for the unit impulse system, basically R equal to 1. So simply C will be equal to this one only, just like we draw here. Okay. Given these functions, if we still want to use the step input, then the steps are the step command in MATLAB. We have to tailor this form into something multiplied with 1 over S. Okay. So if we want to have something 1 over S, then simply we have to multiply S. In this way, this and cancel equal to 1. Okay. So in this way, we're leaving this out. Right now, it's into the syntax. Leaving this out, and we describe the numerator and denominator in terms of these functions, so that it's 2, 1, 0, 1, 1, 1. Can you see the difference between this example and that one? Okay. Now we move on. For the unit ramp input, then R, this one will be 1 of S squared. So like this one. This is our problem statement from control. And then again, and we want to fit into the template, so that means something multiplied with 1 over S. So we tailor this description into this. So leaving this out, then we talk about the syntax. This is the numerator denominator descriptions we're going to use. So that is become like this. So can you see the difference among the three examples here? Good? Okay. So basically this is kind of the MATLAB kind of tips. We can use the simple and the single command, and we can do the things for different command, for the different input command here. Okay. Otherwise, if you don't follow this one, then if you want to on your own and doing very primitive method, then for this case, you simply use this one. And for this case, then you need to look up impulse command from MATLAB. Okay, there's an impulse command. For this one, for this case, there's no such appropriate command in MATLAB. So you have to, if you wouldn't know this tip, then what you have to do is you have to manually calculate C of t by your hand, okay, and do the Laplace inverse. Then finding the description of C of t and then implement that time function in MATLAB. Okay, so that is another feasible way, but this is quicker. Okay, so that is these sections here. This is an example here. So example we can try is this. So if this is the control systems here, and this is the vibration system, and is Gaussian equation is given by this. Okay. And right now for this case, and we have no command here. So right now in this example, right now I'm talking is not control. I'm talking is about vibrations. I simply use this example to demonstrate the techniques we learned. So this is called the free vibration system. Why we call it free vibration? Because this vibration system is subject to no external loading. No external loading, that means we call it free vibrations. If there's any external loading, then we call it forced vibrations. Okay, so this is a free vibration without any external loading. So basically, in terms of control terminology, this system has zero input. Okay, and if the system has a zero input, then basically in our sense, a system that if has a zero input, then in terms of the transfer functions, then suppose have a zero output. Okay, but again here, if you remember the transfer function, in transfer function we assume initial conditions equal to zero, but here it's not. Okay, so again, let me back to the topics here. I talk about the vibration system. So for this exercise, I simply want to know what is the influence of the initial conditions to the response of the system. So which means given the input, given the initial conditions, I want to know the x of t. That's it. So this problem is nothing regarding control. This is the typical the vibration problems. And let me show you how to do it. So again, we take the Laplace transform, and on the individual terms, then we can have this one, and we plug in the initial conditions here and here. We have these descriptions. That is x of s. If we take the inverse Laplace transform on this one, then we would know x of t based upon this. Okay, so that is a doable, and that is an exercise everyone have learned from the topics covered in test 1. Okay, if we want to do it by hand, we can start from here, taking inverse Laplace transform, then we can get x of t. Then once you have that description, you can plot it. On the other side, we can use our example, the step command. I'm going to apply MATLAB using the step command. And my goal is to plot the x of t based upon these functions. So again, you can see in terms of the syntax here, I try to separate one of s, and then in this way the problem description is described about this system here. Okay, I have the one of s, so the original system must be multiplied with s to make it equal. So we together with this one, so numerator should be for this one should be 0.105 and the 0, because this the numerator right now is a second order system. Denominator is 132. So we have this one, we take the step, then we have the x of t plotted. And that is this page. Okay, so this is the x of t. And from here you can see at the initial conditions, the x of 0 equal to 0.1. And initial velocity is positive to a certain way. So we back to the previous page. We check our initial conditions here. So x of 0 is 0.1, and we have a positive velocity. And those things just simply reflected onto here. Okay. And then this is the system x of t due to the existence of initial conditions. So basically you can see that the second order system, initial conditions influence basically decaying over time. Okay, so that is what we coincident with kind of match up with our descriptions. This is the reason why in the transfer functions we don't consider the influence of the initial conditions, because eventually the influence of initial conditions become almost zero. Okay, basically that's kind of decayed by the system damping. Okay, so that is one example. So Scott, we stop these sections.